Physics is fundamentally an empirical science, meaning that its core principles and theoretical models must ultimately correspond with the physical reality of the natural world. Without physical intervention, measurement, and data collection, theoretical equations remain abstract mathematical constructs rather than verified descriptions of how the universe operates. Experimental research forms the vital counterpart to theoretical physics, functioning as the primary mechanism through which hypotheses are rigorously tested, validated, modified, or discarded. The relationship between experiment and theory in physics research is deeply symbiotic. Theoretical physicists use mathematical frameworks to predict new phenomena, establish boundaries for physical behavior, and model complex interactions. However, these predictions require empirical grounding to confirm their validity. Experimental researchers design controlled environments, build specialized instruments, and execute precise measurements to check whether nature behaves as the theories predict. When experimental results align with theoretical models, confidence in those models grows significantly. Conversely, when data contradicts prediction, it signals that the underlying theory must be revised or replaced, driving the evolution of physical understanding. Experiments in physics research serve multiple distinct functions beyond simply checking whether a formula is correct. Discovery-driven experiments explore unknown territories where no comprehensive theory yet exists, uncovering unexpected phenomena that demand entirely new theoretical frameworks. Furthermore, experiments provide direct evidence for the existence of theoretical entities. Historical milestones, such as cathode ray investigations identifying the electron or modern particle accelerators detecting subatomic components, demonstrate how physical intervention grants observational access to entities initially proposed purely through mathematical calculation. The scale and methodology of physics experiments vary dramatically depending on the subfield. On one end of the spectrum lie laboratory-scale setups involving lasers, vacuum chambers, and cryogenic systems designed to probe quantum mechanics, condensed matter, and optics with extreme precision. On the other end are massive international facilities, such as particle colliders and gravitational wave observatories, which require vast engineering efforts to capture rare events or subtle cosmic signals. In astrophysics and cosmology, where direct manipulation of variables is impossible, researchers utilize natural experiments, carefully observing radiation, celestial mechanics, and large-scale structures to test physical laws under extreme conditions. Designing a valid physics experiment requires rigorous control over variables, meticulous calibration of instruments, and exhaustive elimination of alternative explanations or systematic errors. Researchers must quantify uncertainties and ensure that their data acquisition methods can be independently reproduced by other laboratories. This standard of reproducibility is what separates scientific research from anecdotal observation. When an unexpected anomaly appears, experimental physicists must rule out equipment malfunction, environmental interference, and statistical fluctuations before claiming the discovery of a new physical effect. Ultimately, the history of physics demonstrates that progress stalls when theory and experiment become detached from one another. Breakthroughs occur when innovative instrumentation opens new windows for observation, revealing facets of reality that theory had not yet anticipated, or when precise measurements settle decades-long debates over competing theoretical models. Experimentation remains an indispensable tool for physics research, continually anchoring human curiosity to measurable, objective truths about the universe.